Hi everyone, welcome back to Prakasham Tutorials. In my previous videos, I already designed half-wave dipole antenna at a 2.4 GHz operating frequency. Now here in this video, I am going to design folded dipole lambda by 2 design, folded dipole, half-wave dipole antenna design and simulation results. First save the project, right click on the project, save as. Give the name of file name is, now here my file name is FDA folded dipole antenna underscore 2.4 gigahertz. So this is my file name. So my project is successfully saved. So first select the YZ plane. First draw the rectangular port. Select the rectangular sheet. Draw the rectangular sheet in the plane. So give the dimensions of the rectangular sheet and the rename of the rectangular one is port, and change the dimensions of the rectangular sheet, and the calculations of the half-wave dipole antenna already explained in my previous video. At 2.4 GHz operating frequency, the wavelength is 125 mm and lambda by 2 62.5 mm, and upper radiating element length is 31.25 mm, and radius of the dipole is lambda by 120. So lambda by 120 is 1.04 mm. So Y size is 1.04 mm, that is the dipole radius, and Z size is gap, 2 times of the dipole radius, and position is X position is 0 and Y position is half of the Y size value minus 1.04 by 2, and Z position is half of the Z size value minus 1.04 mm. So click the OK button. So this is the rectangular port. Next select the line, draw the line upper port to the lower port. This is the rectangular port and this is the upper port, this is the lower port. So select the line, draw the line from upper port to the lower port. So click on the upper port, move the mouse upward direction, click that position and move the mouse horizontally and click this position. Move the mouse downward direction, click this position and move the mouse leftward direction, this direction, click this position and move the mouse in lower port of the rectangle. So double click on that position. So this is the line, and after that give the rename of the polyline 1, double click on the polyline 1. So rename is FDA folded dipole antenna. So next change the dimensions of the antenna, and this is create line 1, this is create line 1, and this is create line 2, and this is create line 3, and this is create line 4, and this is create line 5. So now change the dimensions of the create line 1 to create line 4. Double click on the create line 1 and the point 1, and this is create line 1 and this is point 1, this is point 2. So this height of the rectangular port is 1.04, gap is 2 times of the 1.04, from origin to this height is 1.04. So point 1 is, so 0 comma 0 comma 1.04, and point 2 is 0 comma 0 comma height of the dipole. And now here the at 2.4 gigahertz operating frequency, the wavelength is 125 mm and lambda by 2. So 125 by 2, 62.5 mm, and upper radiating element length lambda by 4. So lambda by 4. So 125 mm by 4 is 31.25 mm, and subtracting the gap value from that lambda by 4, lambda by 4 minus gap. So gap value is 2 into 1.04. So 29.1 mm. So the upper radiating element length is 29.1 mm. So now here point 2 is 0 comma 0 comma upper radiating element length 29.1 mm minus 1.04 mm. So press the OK button. So that are the create line 1 dimensions. Next change the dimensions of the create line 2. Double click on the create line 2. So that point 1 dimensions are 0 comma 0 comma 29.1 minus 1.04 mm, and point 2 dimensions are, and the spacing between the dipole is, spacing between the half folded dipole antenna spacing is 0.04 into 0.04 into wavelength. So 0.04 into wavelength. Now here the wavelength lambda is 125 mm. So 125 into 0.04 is 5 mm. So the spacing is 5 mm. So 0 comma 5 comma 29.1 mm minus 1.04 mm. So press the OK button. So that are create line 2 dimensions. Next change the dimensions of the create line 3. Double click on the create line 3. The point 1 dimensions are 0 comma 5 comma 29.1 minus 1.04, and point 2 dimensions are 0 comma spacing between the dipole is, folded dipole spacing is 5 comma minus 29.1 plus 1.04. So press the OK button. So that are the dimensions of the create line 3. Next change the dimensions of the create line 4. Double click on the create line 4. So point 1 dimensions are 0 comma 5 comma minus 29.1 plus 1.04, and point 2 dimensions are 0 comma 0 comma minus 29.1 plus 1.04 mm. So press the OK button. So next change the dimensions of the create line 5. Double click on the create line 5. Point 1 dimensions are 0 comma 0 comma minus 29.1 plus 1.04 mm, and point 2 dimensions are 0 comma 0 comma minus 1.04 mm. Press the OK button. So now select the fetal. This is the folded dipole antenna. So now change the width of the line. Double click on this FDA. Sorry. So double click on this create polyline. So now here the type is none. I am selecting the type is circular type, and width of the dipole is 2 times of the dipole radius. So 2 into, now here the dipole radius is 1.04 mm, and bend type is corner. I am selecting curved shape. Press the OK button. So this is the folded dipole antenna. So now change the type of the material. Double click on the FDA. Now here the material is vacuum. I am selecting PEC material, perfect electric conductor material. So press the OK button. So now assign the lumped port excitation. Select port, right click on the port, go to assign excitation, select lumped port, and the full port impedance of folded dipole antenna is 300 ohms. Press the OK button. Draw the new line integration from lower port to the upper port. Press the OK button. Select Don't Renormalize. Press Finish button. So lumped port excitation is successfully assigned. Select the fit all. Now select the box, radiation box. So now here I am selecting open model. So now here in the project manager, so model, right click on the model, select create open region. Now here my operating frequency is 2.4 GHz operating frequency. Change the, type the operating frequency value, press the OK button, fit all. So this is the 3D structure of the folded dipole antenna. Now set the analysis setup. Go to HFSS, analysis setup, add solution setup, select advanced. Now the operating frequency is 2.4 GHz operating frequency. I am selecting maximum number of passes are 12 and maximum delta S is 0.02. So press the OK button and the sweep type is fast and starting frequency is 1.2 GHz, ending frequency is 3.6 GHz and maximum number of points are 101. So press the OK button. Now check the validity. Go to the HFSS, select validation check button. So design is successfully validated. Now start the simulation. Go to HFSS, select analyze all. Simulation is successfully completed. So now observe the results. First observe the S parameter value. Go to the results. Right click on the results. Create model solution data report. Select rectangular plot. S parameter S11 in decibel. Click the new report. So mark the designated operating frequency. Now my designated operating frequency is 2.4 GHz. So at 2.4 GHz, the return loss value is minus 21.84 decibel. Slightly I will change the height of the dipole. We will get minimum return loss value. So now here the height of the dipole is upper radiating element dia length is 29.1 mm. Now here I will change. I am changing the height of the upper radiating dipole element is I am selecting 28 mm. So height of the dipole is changed. Now check the validity. Validate. So design is successfully validated. Now start the simulation. Click the analyze all button. So the S parameter value is updated at 2.4 GHz operating frequency. The return loss value is minus 29.2426 decibel. This is very good value. The folded dipole antenna at 2.4 GHz operating frequency is successfully designed. Next, observe the VSWR value. Right click on the result. Create model solution data report. Select the rectangular plot and select VSWR. Click the new report. So mark the designated operating frequency 2.4 GHz. At 2.4 GHz operating frequency, the VSWR value is 1.0715. So this is excellent value. Next, observe the far field results. So now here the 3D infinite sphere. Pi value is minus 180 plus 180 and theta value is I am selecting 360. So go to the results, right click on the results, go to create far fields report, select the radiation pattern and select the gain in decibel, select the family of the pi values. So the family of the pi values are all values mean minus 182 plus 180. Now here I am selecting the family of the values minus 180, minus 90 degrees, 0 degrees, plus 90 degrees, plus 180 degrees. Click the new report. So this is the two-dimensional gain radiation pattern. Next, select the directivity gain radiation pattern in decibel, directivity 2D radiation pattern in decibel. Click the new report. So this is the two-dimensional directivity radiation pattern. So without decibel, observe the without decibel directivity radiation pattern. So this is the radiation pattern without decibel. So minus 180 degrees, 90 degrees, 0 degrees, 90 degrees, minus 180 plus 180 degrees. Next, observe the 3D polar plot. Go to the results, right click on the results, go to create far fields report, select 3D polar plot. So gain in decibel, click the new report. So this is the gain 3D polar plot. So the gain value is 3.0. So this is very good value. Next, observe the 3D polar plot directivity. So select the directivity in decibel, click the new report. So now where the directivity is 3D polar plot directivity is 3. So gain and directivity, gain is 3 decibel, directivity is 3 decibel. This is very good value. So next, observe the structure with radiation pattern 3D polar plot. Go to the field overlays, right click on the field overlays, select the radiation field, click the gain plot or directivity plot. So now here I am selecting the gain plot, apply. So this is the structure with and this is the structure with 3D polar plot. And this is the top view, bottom view, right view, left view, front view.